Today on How It's Made. Dial thermometers. Whether it's hot or cold, they offer a point of view. Hummus. From the Middle East to the middle classes, we take a dip. Spent fuel containers, nuclear waste storage gets a glowing report. And straw sombreros, trade secrets to keep under your hat. But first, if you need to find out what the temperature is, a dial thermometer is a lot easier to read than a standard glass stem thermometer. A needle points to numbers on a dial, and even from a distance, it only takes a quick glance to confirm that things are heating up or cooling down. All the highs and lows are easy to see on the face of a dial thermometer, and it often comes with tubing to measure temperature from a distance. It's a handy feature for power plants and heating and refrigeration systems. To begin, rollers straighten very narrow metal tubing. Then a blade cuts it to length. As the blade makes the cut, a mechanism pries open the ends. Next, a worker inserts a fitting into a much wider tube that will become the sensor bulb. He secures the bulb in a fixture and welds the narrow tubing to the fitting on the end of the bulb. With the bulb and tubing now linked, production moves to the next stage. The making of the board-on-tube, which is a type of spring. A worker cuts flat, wafer-thin tubing to length. Down the line, they clamp the flat tubes in a device that's on a track. It moves past an arc welder that melts and closes one end of the flat tubes. Here is a before and after comparison. A worker now encloses the tube in a die and drives a pin into its open end. This widens and redefines the opening. He slides it over another pin and activates a mechanical punch press. This fine-tunes the shape and dimensions of the opening. The next worker clamps the tube in another device. He operates a roller to wrap it around a mandrel, bending it into a C shape. This completes the thermometer's board-on-tube spring. The next worker clamps a bracket to the bottom of the board-on-tube. He inserts a small piece of connector tubing to the board-on-tube hole and applies liberal amounts of flux compound. The flux prevents tarnishing of the metal as he melts silver solder to braze the parts together and seal the opening. Now they test it. He pumps gas into several board-on tubes and immerses them in water. If no gas bubbles out of the tubes, it means the tubes are perfectly sealed. The gas pressure also causes the tubes to spring into action. It's this action that will move the pointer on the dial of the thermometer. The next worker attaches a brass connector to the tubing. He brazes them together to create a solid bond. He folds the brazed parts into the curve of the board-on-tube and pushes it into place with a mechanical press. He installs the gear assembly that will translate the linear movement of the board-on-tube into the rotational movement of the thermometer pointer. He screws the dual temperature dial to the board-on-tube assembly. The more detailed and extensive the scale, the bigger the dial. This one is mid-size. And now everything comes together as he tethers the sensing bulb, along with a short fill tube, to the back of the board-on-tube assembly. Using a brazing torch and solder, he seals the connection. He then steam cleans the brazed joint. He buries the bulb in a hot sand bath, which causes any moisture in it to evaporate. Through the fill tube, he fills the bulb with nitrogen gas. To calibrate the thermometer, he plunges the sensing bulb into boiling water and adjusts the pressure of the nitrogen gas until the dial reads 100 degrees Celsius. The fill tube's job is now done, so he crimps it to seal it off. He tests its accuracy by immersing the sensing bulb in numerous controlled baths, each one a different temperature. And if correct, He encloses the inner workings in a stainless steel case. He protects the joint with a special metal spring and clips a clear window to the case. A gasket between them ensures a dust-proof seal. He screws a part called a well to the sensing bulb connector. The well will protect it in high-pressure situations. And this dial thermometer is now ready for the highs and lows of temperature gauging. Cool. Hummus is the original snack food. People have been eating this chickpea dip for hundreds of years. Countries from the Mediterranean to the Middle East lay claim to its invention. But one thing is beyond dispute. As an appetizer or side dish, hummus isn't just a passing fad. Besides being very tasty, hummus is also an important vegetarian source of protein. The word hummus is actually Arabic for chickpea, which is, of course, the main ingredient. The chickpeas arrive at the factory in dried form. They ride a conveyor belt and then spill down onto a long vibrating tray. It shakes out heavier contaminants like pebbles or twigs. The contaminants fall into a bin below, while the chickpeas bounce off the tray and into a tub of filtered water to be rinsed. Still dripping wet, it's onto a conveyor with perforated buckets. The water drains from the chickpeas as they're transferred to big tanks. Each tank holds thousands of chickpeas. They add clean water and soak the chickpeas. After 14 hours in the tank, they swell to twice their size and soften up. They pump the softened chickpeas into big trays, which they stack on a cart. Then it's into a huge cylindrical steam cooker that's been preheated to around 124 degrees Celsius. They bake the chickpeas for just over half an hour. This softens them even more and darkens the colour. From dried beans to soaked and then cooked. They now transfer the cooked chickpeas to the next conveyor, and they're on the way to being ground to a pulp. This is the grinder, now being reassembled after cleaning. It has two sharp-toothed circular blades. One is stationary and the other revolves. A turn screw will force the chickpeas through these toothed blades to grind them up. A quick test confirms this grinder is in working order. Meanwhile, the chickpeas have arrived at a hopper above the grinder. As the chickpeas spill into the hopper, they add water and a blend of sunflower and olive oil, followed by salt, garlic, and other dry ingredients. This mix now flows into the grinding device below and is turned into paste. The next ingredient is tahini. It's a thick paste made from ground sesame seeds. 3 powerful pumps pulverize the tahini to evenly disperse the particles, so it can now be blended with the chickpea mix. Large steel blades revolve to thoroughly mix all the ingredients in a tank and produce hummus. For different flavoured hummus, they add red pepper, more garlic, or other ingredients. After the blended product is pasteurised, a technician takes a sample to test for mould, shelf life, and consistency. She also does her own taste test. If the flavour seems even slightly off, they'll put the product on hold and tweak the ingredients. But this batch gets the nod. Meanwhile, plastic containers are queuing for a fill-up. Machinery moves them forward towards piston fillers. The pistons push the creamy hummus out of nozzles and into the tubs. Now filled to the brim with hummus, the tubs travel under a sheet of plastic film. Hot round irons melt the plastic to seal it to the rims. Suctioning devices swoop down to apply the lids, and the hummus heads towards a roll of adhesive-backed labels. A sensor detects the approach of the tubs and triggers a device with air jets to slap the labels on the lids. The tubs are ready to dispatch to delis around the world. This hummus production is a very smooth operation. Coming up, spent fuel containers. Don't overreact, even though it's about nuclear waste. And straw sombreros. Take your hats off to Mexican milliners. See you after the break. Spent fuel containers are designed to take the heat, the kind caused by the most radioactive of wastes. Use nuclear fuel. These fuel rods are too dangerous to be casually disposed of, but encased in special spent fuel canisters, the risks should be contained. Nuclear waste needs to be stored in massive cylinders until there's a way to dispose of it. These containers start with a big rectangular sheet of stainless steel. A special cutter carves a beveled edge onto it. They feed it to rollers, which curl the sheet into a cylinder. It takes 4 trips through the rollers to really round it out. They tuck a template inside the curve to check the radius. Next, a welder joins the neatly beveled edges to complete the cylinder. This cylinder will be the outer wall of a canister. The canister will fit inside a bigger cylinder called an overpack. Its outer shell is 2.5 centimeters thick, about the diameter of an American quarter. Building a container to hold used nuclear fuel is a many-layered process. The next step involves the lid, made of multiple steel discs, with concrete placed between the steel layers, like a sandwich. High-pressure water jets cut through the thick steel to produce the discs. A computerized tool cuts a groove along the edge of each disc. They also machine the top of each disc to the correct profile and then measure to confirm it's exactly right. Next, a computerized laser slices through more stainless steel plating to produce long, narrow panels. Each is designed to fit together to create a grid of storage cells inside the canister. They line each panel with an aluminium alloy that's neutron absorbent, and they place a piece of steel sheathing on top of that. They weld the steel sheathing to the steel panel, encasing the neutron-absorbent material. Working within a metal framework for guidance, they weld 4 of the lined steel panels together to create a fuel cell grid for one used nuclear fuel bundle. Then they build a 68-cell grid. With that complete, they're ready to piece together all the parts of the spent fuel canister. First, they lower the inner shell onto the base plate. The shell is held steady by a supportive structure as they weld it together at the seams. Moving inside, they install numerous bars to support the fuel cell grid. With the canister now wrapped in plastic to keep it clean, an automated cutter gradually shaves down the rim to trim it to the correct height. Precision is critical. Using a level and a laser, they ensure that the trim job is even and exact. Once they're satisfied, a crane carries the fuel cell assembly over to the canister and then suspends it above the open cavity. It dangles briefly as workers inspect the assembly. Then give it the thumbs up, and the crane lowers the fuel cell assembly into the cylinder. It's a snug fit, with just over a centimetre of clearance between the inner assembly and the wall of the cylinder. This technician inserts a camera into each cell of the grid and scrutinises the image. He's looking for any debris that could hamper the installation of the nuclear fuel bundles. Both the cylinder and the fuel cells have been meticulously cleaned, but the camera inspection confirms that they haven't missed anything. So it's time to put a lid on this nuclear waste canister. It's a trial fit. The lid will be permanently welded to the canister later, once the used fuel rods are safely inside. The canister will then be placed inside the overpack, with concrete poured between the walls. With the lid on, the hazards of nuclear waste are entombed indefinitely, hopefully without any fallout. The word sombrero is derived from the Spanish sombra, which means shade. The expansive brim of these Mexican hats is designed to cast a wide shadow over the face, neck and shoulders. Fancier sombreros are made of felt. Regular ones are woven out of straw. This workshop makes traditional straw sombreros in many styles. This model is called a Winston. This one, an Americano. Here's the Speedy, after the cartoon mouse, Speedy Gonzales. And the Cassidy. These sombreros are handcrafted. The straw is from white palm leaves, which are produced locally. First, workers soak a bunch in water for a minute or so to soften them up. Then, using a needle, they tear strips about ½ a centimetre wide. Then they take 3 strips at a time and braid them together into a single strand. They intertwine several braided strands, making a long braided straw rope. Then they feed this rope into a manually operated press. The press flattens the rope until it's just about 1 millimetre thick. This flattening makes the coarse rope soft enough to sew. With the raw material prepared, hat construction can begin. They take the rope and wind it in concentric circles, sewing one circle to the next. They first make a flat base, then turn the base on its side and keep sewing until they form the cup, the part of the sombrero that sits on the head. They place the cup over a hat block to check the size. They then resume sewing, now working outward to form the hat's brim. Brim width varies by style. They measure to make sure it's the correct size. Once the sombrero is finished, they boil water. Pour in gelatine. Stir until it's completely dissolved. Then soak the hat for about 1 minute. The gelatine penetrates the straw fibres. They then hang the sombrero to dry in the sun for about 3 hours. The workshop has a steel mould for each sombrero style it produces. Workers place the hat on the appropriate mould in a hot press, then close it for 3 minutes. The heat and pressure form the straw to the mould shape. The heat also hardens the gelatine, locking in the shape permanently. Many sombreros have a decorative band encircling the base of the cap. This band, called a scarf, is handcrafted, typically out of leather. Or like this one, out of maguey, a fibre from the stalk of a tropical plant native to Mexico. A few dabs of glue hold the scarf in place. Once a sombrero is finished, the workshop tags it with a certificate stating the model and serial number. Sombrero shapes can vary significantly, but they all share a common characteristic: a wide brim to protect from the blazing sun. Certain models have an extra feature, a cord or leather drawstring, so that the hat doesn't blow away in the wind, because that would be the final straw.
From black holes and neutron stars to meteors and the Big Bang. Investigate the inner workings of the cosmos this Thursday night at 9 on Discovery in a brand new series of How the Universe Works.